Here is the solution for the day 3 BOWERK. Graph this function and graph it on paper by identifying asymptotes, any holes, and any intercepts. This is called a rational function because there's a numerator and a denominator. Both numerator and denominator are polynomials. Now these polynomials are in factored form. Often you'll see this where the numerator and denominator are not factored, and that's the first thing that you end up doing as the student is you factor them. Now to draw the picture of this, we need to identify some key features. One of the features we're asked to identify is asymptotes. There are 3 kinds of asymptotes. One is horizontal asymptotes. Another is vertical asymptotes. And another is slant asymptotes. Not all rational functions have all of these kinds of asymptotes. And there's a procedure that you learn in algebra class to know when you have the asymptotes, as well as what the asymptotes are. The decision about whether a rational function has a horizontal asymptote is done by examining the degree of the numerator and the degree of the denominator. So let's figure out the degree of the numerator and the degree of the denominator. Both numerator and denominator have been factored. When you have the linear factorization of a polynomial, the degree is equal to the number of linear factors. The numerator has 3 linear factors. It is degree 3. If you expanded that by multiplying together those 3 binomials, you would get a polynomial that has in it x to the 3rd power, a 3rd degree polynomial. Now the degree of the denominator is degree 2. It has 2 linear factors. If you performed FOIL on the denominator, you would get an x squared as your leading term, and that's degree 2. To decide if there's a horizontal asymptote, we compare the degree of the numerator to the degree of the denominator. Because the degree of the numerator, 3, is greater than the degree of the denominator, 2, there is no horizontal asymptote. If the degree of the numerator was equal to the degree of the denominator, for example, if both were degree 2, then there is a horizontal asymptote, and the equation of that asymptote is found by comparing the leading coefficient of the numerator to the leading coefficient of the denominator. If the degree of the denominator is greater than the degree of the numerator, then the horizontal asymptote is the x-axis, the line y equals 0. Now, vertical asymptotes. They are found by looking at any zeros of the denominator, because those are restricted values, values that x cannot equal because it would create an undefined situation. Because the denominator is already factored, it's pretty quick to find its zeros. One of the zeros is 3. So a vertical asymptote is the vertical line x equals 3. There is another zero of the denominator, 4. X cannot equal 4. However, please notice that there is a matching linear factor in the denominator and in the numerator. Those cancel away. So when we're considering vertical asymptotes, if the x minus 4's have canceled away, then there is only one vertical asymptote, and it's the line x equals 3. The fact that there is an identical factor in numerator and denominator creates a hole in the graph of the function. The hole will be located at 4, and the y value of that ordered pair will be the value of the function when you substitute 4 in for x while disregarding those factors that cancel away. So 4 subtract 1 makes a 3, 4 subtract 2 makes a 2, and down at the bottom, 4 subtract 3 makes a 1. This creates 3 times 2 makes 6 on top and 1 on the bottom. The result is 6. When we graph this, we're going to create a hole at the point 4, 6. Now let's go back to slant asymptotes. Slant asymptotes are diagonal asymptote lines. They exist when the degree of the numerator is 1 more than the degree of the denominator. And that's what we have here. Degree 3 is 1 more than degree 2. So there is a slant asymptote It has an equation in slope-intercept form that can be found by doing polynomial long division. Because the polynomial on the bell work is in factored form, the first thing I'm going to do is rewrite it by expanding top and bottom. So performing FOIL on the top, x times x is x squared. The outer product is negative 2x. The inner product is negative 1x. That makes negative 3x. And then the last is positive 2. The denominator is the x minus 3. Next, perform long division by dividing x minus 3 into that numerator. X multiplied by x creates x squared. X times x is x squared, and x times negative 3 is negative 3x. Now subtract, creating 0, and bring down that last number, the 2. The 2 is a remainder, which when you do polynomial long division, is written up above as a fraction. However, when you find the equation of the slant asymptote, we don't care what that remainder is. We're only paying attention to this piece right here. So the equation of the slant asymptote is the line y equals x. That's a diagonal line with a slope of 1 goes through the origin. We're also asked to determine any intercepts, the locations where the function would cross the x or y axis. There are two kinds of intercepts. There are x-intercepts, and there is a y-intercept. The x-intercepts are also called the zeros of the function. They are the zeros of the numerator. Again, because the polynomial is in factored form, it's pretty easy to find the zeros of the numerator. One of them is when x is 1, and another is when x is 2. The y-intercept is the value of the function when x is 0. So let's make the appropriate substitution and determine the value of y when x is a 0. 0 subtract 1 makes negative 1, 0 subtract 2 makes negative 2, and in the bottom, 0 subtract 3 makes negative 3. In the numerator, negative 1 times negative 2 makes 2, and 2 over negative 3 is negative 2/3. The function will cross the y-axis at the point 0, negative 2/3. We've identified all of the pieces needed to make a very accurate drawing of this graph. Let's run through our features. There's no horizontal asymptote. I'm not going to draw a horizontal dashed line. There's a vertical asymptote at x equals 3. So crossing the x-axis at 3, a vertical dashed line. There's a slant asymptote, the line y equals x. That is a diagonal line through the origin with a slope of 1. There is a hole at the point 4, 6. Our graph will cross the x-axis at 1 and at 2. And our graph will cross the y-axis at the point 0, negative 2/3. With this information, we can draw in the curves that will be our rational function. If this isn't enough information to make an accurate graph, we can find additional points on the graph by choosing values for x, substituting them in to get the corresponding y values. I'm going to draw the graph using the information I have. So close to the slant asymptote, through these 3 dots, somewhere around here it will curve and come down through that dot, and then approach this vertical asymptote. Now the section up here, alongside this asymptote, it'll come down. When you reach the hole, jump over it, and then somewhere around here it'll curve up and then come alongside this asymptote. Here is the finished graph of that rational function.